Okay, so I left you with sort of an incomplete, well, a smattering of stuff. So I want to fill in some holes and things like that. Let's see. First of all, are there any questions?
Yeah.
Things? Yes.
When you do the expansion like x5 plus x equals 1,
Yep.
you put the epsilon in the exponent of say the x5 term.
Could I put it in the exponent? Yes.
Yes.
That's a wonderful question, and it's really interesting. It opens a whole area of possibilities. Did everybody hear the question? When we were on the first lecture, we took as an example that the problem of finding the roots of that equation. Okay, and we said we would like to do perturbation theory. So there were several possibilities that we considered. One possibility was to insert an epsilon over here. Okay? And what was nice about that possibility is that nothing abrupt happens as you reach the unperturbed problem. Okay? There's no abrupt change that occurs. So the kind of abrupt change that could occur would be that some roots might disappear. Okay? But clearly, as epsilon goes to 0, there are always 5 roots. Okay? And even at epsilon equals 0, there's still 5 roots. Okay? We only looked, by the way, we only looked at the real root. But if we had started with the complex root, then we would have found a perturbation calculation of the complex roots as well. So we could have calculated any of the five roots of the polynomials. Okay. The second thing we looked at was putting an epsilon in front of this term, and that raised a really interesting question. And the question was, you can do perturbation theory, but apparently you can only find one root, because the unperturbed problem only has one root. That, of course, is not true. And the reason is, do you remember that we showed that the roots, the other 4 roots, disappear as epsilon goes to 0 by going off to infinity? Okay? How did they go off to infinity? The other 4 roots, each of the roots, behave like some constant over epsilon to the 1/4, okay, as epsilon goes to 0. Remember, we showed that, okay, and this is some complex constant, okay. So to attack the problem, this way was working. To continue with the problem here, which I didn't explain to you, but while I'm answering the question, I'll mention this too. What we could do is to say, since we know that the other roots behave like some constant over epsilon to the 1/4 as epsilon goes to 0, why don't we make a change of variable? Why don't we say, let x equal, so you notice I'm switching from an asymptotic approximation back to an equality for the moment. And I say, why don't we let x equal y over epsilon to the 1/4? Because that's the natural thing to do. Now, if we substitute this into the equation, we get y to the 5 over epsilon to the 5/4 plus y over epsilon to the 1/4 equals 1. Got it? And of course, we have put an epsilon over here. Okay? Now let's multiply through by epsilon to the 1/4, and you see that we have the problem that reads like this. Now, this is a very nice problem. Okay? Because now you see the way epsilon naturally wants to be inserted into the problem. It doesn't really want to be over here. Okay? It really wants to be over here. And now, when epsilon is equal to 0, this equation reads y to the 5 plus y is equal to 0. This is the unperturbed problem. Got it? And now, we can find all 5 roots of this equation. Okay? And you can see that, well, if y is not equal to 0, we can divide out y. Okay? We see that there's, of course, one solution is y equals 0. But the other 4 solutions satisfy y to the 4 plus 1 is equal to 0. Okay? And we can expand about 0. That would be the first term in the series. It's a perfectly good first term in the perturbation series. Here are the other 4 roots. We can develop series in general of the form sum from n equals 0 to infinity a sub n epsilon to the 1/4 to the n. So epsilon to the 1/4 is the natural small parameter for this problem. Okay? And of course, for this root, all that this means is that a0 is equal to 0. That's all. Okay? And for the other 4 roots, a0 is the complex solution of that algebraic equation. Okay? But you've asked a really interesting question. You've said, wait a minute, case 3, why don't we put it up? There's another place we could put it. Notice we've now put it here, here, and when you put it here, it naturally goes over here. Okay? But another possibility is, say, to put it up in the exponent. This opens an absolutely fascinating possibility, because what you're suggesting is, why don't we consider something like, well, we can solve x plus x equals 1. We can solve that problem. Not very hard. Okay? So why don't we consider putting epsilon up here? Okay? Now, epsilon plays a very, and the answer to your question is, of course, we can do exactly as we did before. You notice the unperturbed problem reads 2x equals 1. Okay? So the solution is x equals 1/2. That's the first term of the series. And now we can look for a solution, x of epsilon, is a series of the form a sub n, epsilon to the n, same as before. Okay, exactly the same as before, sum from 0 to infinity, where a0 is now 1/2. And we can substitute this into the equation, expand in powers of epsilon. Of course, we're going to get logs of 2 all over the place, but who cares? It's just a number. And it turns out this is a very, very powerful way of doing perturbation theory. Okay? And the radius of convergence of this series will be 1. Now, of course, at the end of the problem, we want to set epsilon equal to 4. So again, we're going to be outside the radius of convergence. Okay? But we're going to learn what to do about that. That's the objective for the next few days. Okay? Yeah?
So just kind of pointing out here that we're talking about the radius of convergence in the epsilon plane, right?
In the epsilon plane.
Yes.
That's right. So the radius of convergence is determined, so this is the complex epsilon plane, and there's a singularity at -1. Okay, and that's the reason that the thing has a radius of convergence of 1.
Because
Okay.
yesterday we saw 2 expansions in the tutorial.
Mhm.
One as an epsilon, as a Taylor series in epsilon, and another one is a Taylor series in x.
Right.
And we compared those two.
That's right. That's right. And as a Taylor series in powers of epsilon, this was the second order differential equation with an e to the minus x in it. That's right. As a series in powers of epsilon, the radius of convergence is infinite, just so long as x is finite. Okay. Also, as a series in powers of x, the radius of convergence is infinite. Okay, in both of those cases. Okay. But we're not worried about the fact that we might want to evaluate this series at epsilon equals 4. That's not a problem. because we're going to learn how to sum divergent series. That's a meaningful thing to do. But this general idea of putting an epsilon in the exponent is fantastic. So let me give you an example. Okay, have any of you seen? What's a good example? Have any of you seen the Thomas Fermi equation, or have you heard about it? No? Okay, the Thomas Fermi equation is a semi-classical approximation to the charge distribution in an atom, in a nucleus of an atom. Okay, so the charge distribution is the charge in an atom is not located exactly at the center. Okay, it's not at a point. It's actually distributed. Okay, and the distribution is governed by an equation that reads y prime prime equals y to the 3/2 over the square root of x. This is called the Thomas Fermi equation, and there's a boundary condition. Y of 0 is 1, and y of infinity is equal to 0. And if you solve the equation on a computer numerically, you'll see that the solution looks like this. Here's what this is x. Here's y, and the solution behaves like this. Okay, and as you expect, the charge distribution goes to x is the radius of the atom. Okay, and the charge distribution is highest at the center, and then it gradually decays. Okay, so this is a second-order differential equation with the boundary condition at 1 and infinity. So this is a boundary value problem, and nobody knows how to solve that. Okay, looks simple enough. Maybe it's only 2 terms, but it's hopeless. Okay. And in fact, solving this numerically and getting this curve is also very difficult. So if you're interested, I don't want to give you instruction on numerical analysis here, but I can tell you how you go about solving that equation. It's very non-trivial, okay, numerically. And that's because this equation is unstable. But suppose a guy walks up to you in the street and says, I've been working on the Thomas Fermi equation, and I dropped my computer, and it doesn't work, but I'd really like to have a good approximate solution to this equation. Okay. So what do you do? Okay, this is a very, very hard problem. And it's nonlinear. Okay, y to the 3/2 here. So this is a very, very difficult problem. What do? Aha! You do exactly what you suggested. Okay? You say, I can solve the following unperturbed problem with the same boundary conditions. I can solve y prime prime equals y. Okay? And with these boundary conditions, same boundary conditions, y of 0 equals 1, y of infinity is equal to 0, what's the solution to this problem? This is a linear problem, of course. What's the solution here? Say it again.
E to the power of minus x? No,
E to the
no,
minus
that's
x.
not
That's right.
right.
That's right. So the solution, so let's call this y0, and the solution is y of x equals e to the minus x. Okay? Very good. So can you read that? E to the minus x. So here, the unperturbed problem, y0, the unperturbed problem is solvable, and now let's use your trick. So let's consider the equation y prime prime equals y times y over x to the epsilon. Okay? And let's look for a solution. Y is the sum of y sub n times epsilon to the n, where y0 is e to the minus x. And all we need is about 1 or 2 terms, 2 terms in this series beyond y0, gives you a fantastically accurate approximation. So what is epsilon in this case really? What is this doing? This is measuring how nonlinear. Epsilon is a measure of the nonlinearity of the problem. Okay? That's the advantage of putting it up in the exponent, because epsilon has a meaning. Okay? As you turn on epsilon, the problem gradually moves away from the linear case, which is exactly solvable, to a nonlinear case. And you can use this in all sorts of possible contexts. For example, suppose you were solving, let's see, who knows what this equation says? Does anybody know this equation? It's a nonlinear wave equation. Say it again?
In optics?
Say it again?
I
No,
don't know.
I think you had it.
Korteweg de Vries?
Yes. This is the Korteweg-de Vries equation. Korteweg-de Vries equation. It's a beautiful nonlinear wave equation. If we had lots of time, we could talk about things like this. Fantastic equation. This, if I take this away, take one derivative with respect to x away, and put a minus sign here, then this becomes the Burgers equation. Okay, again, a beautiful nonlinear wave equation that exhibits shocks and so on. And people use this equation here, the KdV equation, to study solitons and the scattering of solitons and so on. Wonderful equation. If you don't know about the KdV equation, you'll have something wonderful in store. You'll see. You'll love it. Okay, but this is a nonlinear PDE. And if you were looking for a way to solve this equation approximately, we could use your technique again. We could say, raise this power, this u, we could raise this to the power epsilon. And when epsilon is equal to 0, this equation is what this linear equation results, right? And we can solve that by taking a Fourier transform. Okay? So this technique is very powerful. And if you're interested in particle physics or quantum field theory, and you've had some stuff, you might consider the Lagrangian grad phi squared plus, say, m squared phi squared plus g phi to the 4. Okay? And what might you do here? You would say, gee, if this term weren't here, we could solve this equation, because this is a free field theory. It's just a free theory. It's like a harmonic oscillator. And it's this stupid term here that makes things so difficult to solve. All right, you say, fine, we'll replace this by phi squared times phi squared to the epsilon. Okay, and we'll gradually turn on epsilon. And we'll expand in powers of epsilon. And when epsilon is equal to 0, you have this theory, free theory. And already, you can see that when epsilon is equal to 0, the mass in the theory has shifted. The mass term has shifted. So a renormalization is built into the theory. Already, you can see the renormalization, the mass shift in the theory. Okay, so this is fantastic. And the possibilities are endless. This is very, very rich thing to study. This, you can mine this for years. You could spend your life playing with this idea. Yeah?
Why doesn't quantum field theory textbooks do that? I've never seen that in
Because they're boring? I don't know. No, I mean, because, no, the answer is one word. Tradition.
Oh, I see.
Okay? It's just not traditionally the way people go about. You know, this theory, if you put in an epsilon, you can develop a whole set of Feynman rules to study the theory. There's a whole expansion and so on. There are, if you look around, you'll see that there are papers on this idea. Okay? But it's buried. It's in part, it's used in solid state as something called the replica trick. And so people have looked at things related to this. But so this is a very, very rich idea, very interesting idea. Okay, let's see. Okay, so let's see. Any other questions? Anyway, that's a fascinating thing, and maybe we'll talk about that. Okay, maybe we'll, if you like, if we have some time, maybe we'll spend the lecture talking about that, because this is something that interests me a lot. And it's a very, very rich and interesting thing to do. Okay. No, I can't resist. I will say one thing. So you might say, yeah. You might say, why did I say phi squared to the epsilon? You know why I did that? Because phi is a field, and it could be positive or negative. Okay? And if phi were negative, we would be raising a negative number to a power epsilon, which becomes complex. A negative number to a fractional power becomes complex. Okay? So it might be complicated. And you might think that you'd have to put in a phi squared there. But some of my current research is recognizing that that's not true. In fact, it's better to make it complex. And so you might say, in quantum mechanics, let's consider the Hamiltonian h is equal to p squared plus x squared, just in quantum mechanics. What's that Hamiltonian? I mean, what does this represent physically?
Harmonic oscillator.
Harmonic oscillator, okay. Now, what happens if we multiply that by ix to the power epsilon? Okay? So now, this is explicitly complex. And as I turn on epsilon, the Hamiltonian is no longer Hermitian. And it turns out that it doesn't matter, that it's not Hermitian. And if you look at the eigenvalues, so here's epsilon, and here are the eigenvalues. When epsilon is equal to 0, the eigenvalues of this Hamiltonian are, this is usually twice the harmonic oscillator. So the eigenvalues are 1, 3, 5, 7, and so on. Okay, they're odd integers. Okay, and as epsilon increases, what happens is the eigenvalues remain real and positive. And they remain real, positive, and discrete for all positive values of epsilon, which is really strange because when epsilon is equal to 2, for example, here are the eigenvalues. Okay? What, you say? Hold on a minute. You're talking about an upside-down potential because for epsilon is equal to 2, the Hamiltonian is p squared minus x to the 4. How could it be that a potential that looks like this has bound states whose energies are up here? And the answer is it does. And I'm not going to explain to you why that's true. But if you want to know, we can chat after class. Okay, any other questions? I love crapping around. Okay. All right, so let's see, back to work. We were talking about how to solve eigenvalue problems. And the eigenvalue problem that I used for illustration, the simple eigenvalue problem, was the Hamiltonian h is AB plus epsilon times CC. Okay, which is the Hamiltonian A epsilon C B. Okay? And what I showed you was that the eigenvalues could be thought of as branches, that's a technical term, okay, as branches of a single function, E of epsilon, which we can call an energy function, which had the form, I don't know if I can remember it exactly, but it was something like, what was it, A plus B plus the square root of something like A minus B squared plus 4c², was it epsilon squared? Something like that? Is that what it came out to be? Something like that.
Plus minus and plus.
Yeah, now we don't have to write plus or minus, okay, because this is a square root function, okay? Now, you've had, if I understand correctly, you've had just a brief introduction to complex variables, okay? And the first thing I want to do, a little hole that I want to fill in here, is to make sure that you all understand enough complex variables to understand why I don't need to write a plus or minus sign here. Okay? So in general, in complex variables, when you teach a course in complex variables, what do you do first? First, you explain what the complex number system is. Okay? So we generalize from real variables to complex variables. Instead of the real number line, you generalize that to the complex numbers, okay, which have the form, you know, x plus iy. So the complex number z can be represented as points in a plane instead of x, which are points on a line. Okay, so that's fine. So you introduce the complex numbers. And the second thing you do is you introduce complex functions. Okay, so what's an example of a complex function? F of z equals z, okay, or z squared, or something like that, or then you can talk about rational functions, you know, z plus 1 over z cubed plus 14. Okay, so these are elementary complex functions. And then the next step in making up complex functions, it occurs to you, well, we have a function called square root of x, okay, which you learned in high school. And what you learned in high school is that there's a button on your pocket calculator that has a picture that looks like this. And if you push the button, it produces a number. Okay. So the question is, can we define a function square root of z? Okay. It turns out this is the first non-trivial aspect of complex variables, a really, really non-trivial aspect of complex variables that doesn't have an analog in real variables. In fact, what you learn is that this function square root of x in real variables that you learn is nonsense. Okay? It's impossible really to explain what the square root of x is properly. So this is where complex variables becomes essential. So why is it that this is such an interesting function? So what you learn is this. One way to represent a complex number z is in polar coordinates. This is the orthogonal representation. You know, this is the x plus iy, the usual simple representation. But there's a polar representation, which can be written as r e to the I theta. Okay? So in complex variables, here's the complex z-plane. Here's x, here's y. Here is a point in the complex z-plane x plus iy, okay? And you can imagine that its coordinates, you know, are x, y. But a polar representation of this same complex number consists of writing down r, which is the distance from the origin to that point, and theta, which is the angle, okay, from the real axis up to the radial line, okay? Okay, and what's the advantage of a polar representation? Well, if you have two complex numbers, z1 is r1 e to the I theta 1, and z2 is r2 e to the I theta 2, then z1, z2 is r1, r2 times e to the I theta 1 plus theta 2. And you learned that, right? Everybody, I assume you're all comfortable with that, right? Okay, great. So if you multiply two complex numbers, you multiply the modulus, but you add the angle. Okay? So you add the arg, this theta is called arg z, and you add the angle, the polar angle. Okay? And that's very nice. So why is it so nice? Because this provides a natural way to define the function square root of z. You might say, how in the world are we going to define this function square root of z? So you say, it's obvious. When I push the button on my calculator, if I put 3 into my calculator and I push the square root button, out pops, 1.732, so on like that, right? And how do I know it's the right answer? Because if I take 1.732 and so on and square it, I get back 3. Okay? So I have to think of, if I'm going to define this function square root of z, I have to think of a way of writing down something here such that when I square it, I get back z. Okay? So it takes you 2 seconds and you say, look, if z is written in polar form, e to the I theta, then I will define square root of z to be the square root of the modulus, and that's okay, right? Because r is a real positive number. And to find this, all I do is push the button on my pocket calculator, and out pops, 1.732. Okay? E to the I theta over 2. And how do I know this must be the right definition? This is the definition of the function f of z, equals the square root of z. How do I know that's the correct definition? Because if I square this, I get back z. If you don't believe it, watch. Square of the square root of r times e to the I theta over 2. Following this rule, right, de Moivre's theorem and all that kind of thing, is r times e to the I theta. So this must be the right answer. But this is fraught with difficulty. What's the problem? Okay, what's the problem?
You haven't defined the theta carefully.
Right. That's right. You've said it very tersely. That's exactly right. I have to be very careful in defining theta. Okay, you're right. Okay, so let me illustrate what goes wrong. Okay, so what goes wrong is, suppose we say this is theta is equal to 0. Okay, and suppose we take, just for fun, suppose I take r equals 1. Okay, so I take the number, this is z equals 1. And by this definition over here, if this is theta is equal to 0, I conclude that the square root of z equals 1 is 1, right? Because the definition is that I divide 0 by 2, so I still have 0, right? And I take the square root of 1 using my pocket calculator, and I get 1, right? And I conclude that the square root of 1 is 1. Now I smoothly, very, very smoothly, rotate around like this, increasing theta. Okay? So for example, when I get all the way around to minus 1, I have increased the angle, theta is now pi, and I conclude that the square root of minus 1 is e to the I pi over 2. You all see that? So I conclude that the square root of minus 1 is I. Okay? And I keep going, gradually increasing theta until I come back to this point. Now, the angle, because I've been increasing theta all along, when I come back to this point, theta is now 2 pi. It's not 0 anymore. And therefore, I conclude that the square root of 1 is equal to e to the I pi, which is minus 1. Wait a minute! I'm defining a function. A function is something that has a unique answer, okay? And I'm not getting a unique answer. Okay? I can't have two answers. If it's multiple valued, it's not a function. Okay? So I begin by saying the square root of 1 is 1. And I go all the way around smoothly and come back to the same point. and I conclude that the square root of 1 is minus 1. Contradiction. So it looks like I've died. Okay. So what do? I do something amazing. I say, and it's political, by the way. This is entirely political. I say, at some point over here, I am no longer, I draw a line, starting at the origin and going off to infinity. And I say, when I cross this line, I am no longer on this sheet, the original complex plane. I'm on a new complex plane. Okay? So I imagine that I have two complex planes. Here is, here's the first complex plane, which I call the first sheet of a Riemann surface. And here's the second complex plane. Okay? And when I cross this line, if I start over here at theta is equal to 0, and when I cross that line, I am officially no longer on this complex plane, but rather I come out over here. I'm on sheet number 2. Okay? And I go all the way over to here, and I'm perfectly happy because I'm on a different complex plane. I'm not on the original complex plane. I'm on a different complex plane. I'm perfectly happy to say that on this complex plane, the square root of 1 is minus 1. And this explains why it is that you learned in high school that there are two possible answers when you take the square root. Okay? It's really because the square root function is a complex function, and it is required to be defined on a Riemann surface having two sheets. If I keep going and I go around again and I cross that line, I don't come out here, rather I come out over here. And when I come back to this point, once again the square root of 1 is 1. Okay? So on this complex plane, the square root of 1 is 1. And on this complex plane, the square root of 1 is minus 1. And the square root function is not defined on a complex plane, but rather it is defined on a pair of complex planes. It must be, otherwise it's not a function. In fact, not only is the square root function now single valued, so there's a unique answer for every value of z, but it is continuous. It's a continuous function. And why do we want it to be a continuous function? Because ultimately, we have to take a derivative. We want the functions that we're defining to be differentiable. And if they're not continuous, they certainly can't be differentiable. The thing that students find it very hard to understand is, why did you put the cut over here? This is called the cut. Why did you put it over there? The answer is you don't have to. That's a political choice. Okay? So if you look at a map, imagine an alien is approaching the Earth. Okay, and he looks down on the Earth and he sees the ocean, he sees the land. But then an Earthling shows him a map. Okay, and there's a line like this, and here's the U.S. over here, and here's Canada over here. I forgot to tell you, this alien walks on his head. Okay, his head is upside down. So he sees Canada over here, and he sees the U.S. over here. Okay. All right? So, but when the alien looks down at the Earth, the alien doesn't see a line over there. This is just a political designation. This is where the U.S. ends and Canada begins. Okay? So we, as political people, we can put this line anywhere we want. And it doesn't have to be a straight line. It can be a wiggly line. Okay? Of course, usually for convenience, we make it a straight line, just for simplicity. So usually, we might say, there's a branch cut over here and a branch cut over here. Okay? But it has to be the same line. So if you cross this line going that way, you come out over here. If you cross this line going that way, you come out over here. Okay? Now, are there any questions about that? Okay, so now the function that we came up with is a particularly interesting function because this function that we came up with here, this is a particularly interesting function because it's not the square root of epsilon, but rather this square root has the form the square root of epsilon minus a times the square, times, say, capital A and epsilon minus capital B. It's the product of two square root functions. Okay? Not just one square root function. So there are two branch cuts. So in the complex epsilon plane, there is a branch point here, and a branch point here, and here. Okay? So these branch points are located at epsilon is equal to plus or minus I times whatever, a minus b over 2c. Okay? These are the locations of the branch points, and the branch cuts have to be drawn in the same places so that it's a product of two independent square root functions. Okay? When you cross this line, you come out over here. If you should cross this line, you come out over here. Okay? And you know what a Mobius strip is? You all know what a Mobius strip is? You take a strip of paper and you give it a twist and glue the ends to each other. And when you go around once, you come out on the other sheet. If you go around again, you come back on the first sheet. Do you know what I'm talking about? Yeah, I can give you an illustration. Okay. See, this is a cup of, I better not spill this. This is a cup of tea, right? I go around once, and it's not the same. My arm is twisted, and it hurts, okay? And now I continue going in the same direction around again, and now I'm back to the beginning. Okay? So this is so I'm a Mobius strip, in case you didn't know that. It's a two-sheeted surface, and if you go around once, you do not come back. So I'm going around in this direction, I'm rotating this way. I do not come back to the same physical configuration. But if I go around again in the same direction, I do. Now I'm back again. Okay? And you can't say where it was that I left the first sheet and entered the second sheet. That's a political designation. Okay? This sort of stuff represents the dangers of drinking and deriving. You understand that? Okay, so a simple way to draw the branch cuts, a very nice and elegant, simple way, is instead of having these lines go all the way off to infinity, one clever thing you can do with square roots, and only with square roots, I warn you, not with cube roots or logarithms or something, is that you can just connect these 2 points. And if you cross this line, instead of coming out here, you come out here. Okay? And what did we learn? There are 2 sheets in the square root function. One sheet corresponds to, in effect, putting a plus here, and the other sheet corresponds to putting a minus. But that's not true, because plus and minus doesn't mean anything here. It doesn't mean anything because it depends on how you define the square root in the first place. Okay? And so we have 2 sheets, and the function e of epsilon is defined on a 2-sheeted Riemann surface. So what do we mean by the first eigenvalue? The first eigenvalue, so eigenvalue number 1, comes from evaluating the function E of epsilon on the real axis, because we want the energies to be real, okay? And we want the parameter epsilon to be a physical parameter. We want it to be real. So on the real axis on the first sheet. And what do we mean by E2? We get E2 if we evaluate this function on the real axis on the second sheet. In fact, if we evaluate it, remember, this is the epsilon. This is the epsilon Riemann surface. At epsilon equals 0, what we get is E1. Right at epsilon equals 0, we learn that E1 equals A. And right at epsilon equals 0, we learn that E2 is equal to B. So where do we get quantization? Quantization really means that we're evaluating a single function called an energy function on a set of sheets that constitute a Riemann surface. That's why we think the world is quantized. So if you imagine a parking garage, which is perfectly smooth, if you take a saw and slice right through the parking garage, right along the real axis. If you walk into a parking garage, you'll see a yellow stripe that represents the real axis. And if you slice through the parking garage, what you'll see is a bunch of levels, discrete levels. And because we're very narrow-minded and we only think in terms of real variables, we think that quantum mechanics has quantized energy levels. Okay? But in fact, if you extend this to the complex plane, the energy levels are not discrete and not quantized. There's only one energy function, and it smoothly goes from one energy level to the other. Okay? If you drive around the parking garage and come back again to that yellow line on the second floor, that's the second energy level. If you drive around again, that's the third energy level. So, okay, that's why we think quantum mechanics is quantized. Okay, yeah.
But doesn't depend this nice and illuminating interpretation on your choice of epsilon, where you put it? And so,
where I put the branch cut, you mean?
No, the epsilon into your equation.
Oh, sure.
Yes.
Of course,
So,
of course. So I get a different. That's right. So if I put epsilon into my Hamiltonian in a different place, then I'm going to get a completely different Riemann surface.
Yeah.
That's right.
So
That's absolutely right. But when epsilon, and so why do I get a Riemann surface? It's because my Hamiltonian is no longer Hermitian when epsilon is not real. Okay, it's only Hermitian if epsilon is real. Okay, so if I stick with real epsilon, I have well-defined real eigenvalues. And now what I'm doing is generating some sort of Riemann surface that connects all of those real eigenvalues. Okay, and we might argue that for the cases when epsilon is complex, the Hamiltonian is no longer physical. It's no longer a physical object. Okay? So what we have done is we have extended the real axis where there are physical eigenvalues, okay, into the complex plane, and we've seen that these eigenvalues smoothly deform into one another. Okay? However, let me tell you something interesting. There is some work that is being done. In fact, there's a paper that was just put on the web just a few weeks ago, where they can actually, in the laboratory, move around in the complex plane. And they do this by looking at the modes of a microwave resonator. So you make a microwave cavity, okay, and you can change. So this is a number of people. There are about 5 or 6 authors on the paper. It's absolutely beautiful work. And so I guess the principal, the senior author on the paper is Richter, but in fact he didn't do most of the work. The younger people did them. the hard work. This is very hard to do this, but you can make a microwave cavity, and you can put microwaves into the cavity using an antenna. Okay? And then you can vary the parameters of the cavity. And the parameters of the cavity are these epsilons. And if they actually have more than one epsilon, and they can move, and they look at the modes, and there are, of course, thousands and thousands of modes. And as you vary the parameters, you can measure the energy levels, the eigenvalues, the modes of the microwaves in this cavity. And you can actually see them go around in the complex plane and see one energy level analytically continue to another energy level. It's absolutely beautiful work. It's just come out. It's fantastic. I mean, you can actually do this in the laboratory.
So,
yeah.
What do you mean when you say that one energy level analytically moves to another?
In the sense
how do
that,
they measure
so
complex
over
energy?
here, if we start at a value of, let's take epsilon equals 1, okay? Say epsilon is 1. Remember, this is the complex epsilon plane. And the epsilon, the energy function is explicitly written down over here. Okay? So that gives you the energy for that real value of epsilon. Okay? Now, imagine that you have the ability, because you have some microwave cavity and you can adjust the parameters of the cavity. You know, you could stick junk into the cavity, you know, put a little magnet in the cavity and put absorbers and reflectors and all kinds of things. Okay. So you can vary the parameter. And as you vary, in this case there's just one parameter, epsilon, but there could be lots of them. And the eigenvalue moves. Okay? Now I vary the parameter. If I were to vary this parameter and go around like this, keep varying the parameter and come back here, what would happen? I'd come back to exactly the same eigenvalue.
Okay,
But if I vary the parameter like this, and I cross this branch cut, then I come out over here. And if I then return back to the original, exactly the original Hamiltonian, the parameter has the same value that I started out with, 1, say. Now, I have a different eigenvalue. So one eigenvalue smoothly and analytically continues to a different eigenvalue.
Okay, but is the energy eigenvalue actually complex during this?
Yes, of course.
And how do they measure a complex energy?
It turns out that you can infer what is going on by looking at interference patterns, and it's very interesting. I'll let you can read the paper.
Yeah, sure.
Okay, it's just a few weeks old. Okay,
Super.
so it's fantastic. Yeah.
If the branch cut is arbitrary, what defines physically the choice of branch cut? Because if we
as political animals define it. In other words, where do we put the border between the United States and Canada?
yeah, I mean, but
Frankly, what I would do if I had to draw the border, I would draw it like this. Okay, so the United States, you know, comes down here, and here's Texas and California, something like this, and Canada is up here. What I would do is draw the border something like this. I would say. Okay, I would call this one country. And I would call this stuff the other country, because they don't vote the right way. But we're political animals, and we define the borders wherever we want. If you look down from an airplane, you can't see a natural border. There isn't any natural border. We choose when you're on the first sheet and when you're on the second sheet.
So,
Yeah.
so I just had a comment. Is that if you deform the branch cut in such a way that the first path actually intersected that branch cut would intersect it twice. And
If you
therefore-
deform, you mean if you move this branch cut around?
No, on the right hand side, you know, the big
This.
curve where you don't actually come back to the first eigenvalue.
This one here.
Yeah.
Yeah.
But if you deform the branch cut such that that path now intersects with that branch cut, but we will always be intersecting twice.
Exactly.
And therefore we'll always come back to the first eigenvalue.
That's right. This path always will come back to this point. even so, if I drew the branch cut a different way, say like this, I've crossed it twice. So it would look like this. Here I've left the first sheet, and I've come out on the second sheet, and then I've gone down here, come back on the first sheet, and then come back to the original point. Okay?
Yeah, but to connect the points was our choice, right? To connect the two roots was our choice. So
What was I'm sorry, I didn't.
our choice
It was our. What was our choice?
to connect the two roots.
No, that's right. We have a right to do that. We could either connect it or not.
Yeah. So
We can think of this branch cut here as going all the way up to infinity, and then going around at infinity to this one and coming back again. And then we can push that branch cut back into the finite plane continuously, deforming the branch cut until it looks just like this. So all of those are perfectly acceptable choices. It's just our designation. You are now officially in the United States, you are now officially in Canada, because you've crossed a branch cut. And we can put Canada and the United States anywhere we want.
In one of the tutorials, we did the point at infinity, how it can be mapped onto on the Riemann sphere. So
Right.
that basically is interpretation.
Yeah, that's right. And that's a fancy way of, very fancy geometrical way of doing it. Okay. The main thing to remember is that when you do perturbation theory, the perturbation series does not typically have an infinite radius of convergence. Typically, a perturbation series has a non-infinite radius of convergence. When you did this tutorial yesterday, you did perturbation theory for an equation of the form y prime prime, now remind me, e to the minus x times y. You studied a problem like this, and you put an epsilon over here, and this is one of these rare cases where the perturbation expansion has an infinite radius of convergence if x is finite. Okay, but that's almost never happens. If there's a finite, a non-infinite radius of convergence, what determines the radius of convergence? Typically, it's a square root branch point. Okay? Where one solution deforms into another solution. Typically, that's what happens. Okay? And in fact, the most common thing to happen is that the radius of convergence is 0. Okay? And that's what happens in quantum mechanics. Okay? And because the radius of convergence is 0, it means you end up typically with a divergent series. Okay? But what I want to do now is I want to show you how to sum a series. Okay, now this sounds stupid, right? Because you learned that back in elementary school. So let's see. Okay, so this is really, this sounds, I know this must sound stupid to you, but what we have to talk about now is, whoops. What's that? All right, what we have to talk about now is when somebody gives you a series like this, how do you sum the series? Okay, now if you ask a guy, if you just walk down the street here in Waterloo, just stop a random person, and you say, I have a series of this form, okay, how do I find the sum of the series? The guy will say to you, you must be an idiot. This sum is a sigma, the letter S, okay? S means sum, okay? So you're supposed to add up the numbers, right? So you're supposed to write down A0, and then you add on A1, and then you add on A2, and you keep going, and if the series converges, the partial sum, so if you sum this all the way up to an, we call this the partial sum, Sn, of the series, okay? And the guy in the street will say to you, it's obvious what you do. If the series converges, that means that the limit as n goes to infinity of S sub n is equal to the sum of the series, S, period. What else? Okay? And you say to the guy, well, I have a problem. Okay? My problem is that the series I'm adding up is 1 minus a half plus a third minus a fourth plus a fifth, and so on. I have that series. Okay? Now, first question is, does this series converge? You say yes. Why does it converge?
There is this lattice criterion that says that every monotonously decaying zero sequence with alternating signs gives a convergent sum.
Bravo. Bravo. It's basically the alternating series test. If the terms in the series are monotone decreasing and they're alternating in sign, the series converges. You're absolutely right. Great. Oh, this is fun. All right. Did everybody understand that? It's the alternating series test. The series converges. All right, so here's the second question. What does it converge to? Oh. Does anybody know? Yeah.
Logarithm of 2.
Very good. Okay. This converges to log of 2, which is 0.693. Okay. Great. So it converges to log of 2. All right. Suppose you listened to this guy on the street and you started to add up these numbers. How close would you get to the square root of 2?
The size of the term after you stop.
It's hopeless. In fact, if you allowed a supercomputer to run all night long adding up this series, you'd never get to the square root of 2. You could never calculate it to more than 4 or 5 decimal places. It's just ridiculous. So, in fact, the lesson to be learned is one of the dumbest things you can do is what the guy on the street told you to do. It's amazing to me, very few people know what I'm about to tell you, but what I'm about to tell you is so simple. Okay? So the first thing I'm going to tell you is what Mr. Shanks told us. Okay, so Mr. Shanks says, look at the partial sums of this series. How will they behave? So if you make a plot, of S sub n as a function of n, what will we see? What will we see? Okay, so here's n equals 1, 2, 3. What will we see? We know that the series is going to converge to the log of 2, which is whatever, 0.693, something like that, right? What will we actually see? Well, the first partial sum is just 1, right? So it'll be up here. And the second partial sum is 1 minus a half. So it's 0.5. So it's below 0.693. And then the next partial sum is above, and the next partial sum is below, above, below, above, below. So it's oscillating about the answer. So Mr. Shanks says, let's make a model of this series. Okay? So as a model, he says, suppose the partial sums have the form of the sum of the series, and maybe we'll get confused with that letter. Why don't we use the letter L for the limit of S sub n? Okay, so that's the sum of the series. This is the thing that this is the limit here, this limiting value. We'll call this L. Okay? Okay, you following me? So it's approaching some limit, but you notice that it's oscillating about the limit. And as a model, as a simple asymptotic model of this limit, we'll say that it has the form a times b to the n. And we'll think of b as a negative number, so that it's oscillating about this limit. So we'll think of b is negative and less than 1. So as n gets bigger and bigger, the oscillations get smaller and smaller. Now this is not exactly correct, is it? I mean, this partial sum does not have this form, but that's a very simple model of an oscillating series that's tending to a limit. Okay? So accept this for the moment. So then, Mr. Shanks says, S stands for Shanks. Okay? So Mr. Shanks says, in this case, we don't care about A or B. We only care about the limit. Got it? So let's do the following. Let's write down Sn is L plus A B to the n. And Sn minus 1 would be L plus A B to the n minus 1. And Sn plus 1 is L plus A B to the n plus 1. You agree to that, right? And then he does something that you should never do when you're teaching in a classroom. Do not do the following. Don't do that. Terrible thing to do. Okay. Next, let's write down the ratio of the middle term the middle equation divided by the top equation. Okay? So Sn minus L divided by Sn minus L divided by Sn minus 1 minus L. If you divide these two, what do you get? B, right? That's just B. And what do you get if you divide the bottom equation by the middle equation? You get Sn plus 1 minus L divided by Sn minus L. You agree? Okay, very simple. Okay, great. So now, if you just forget B here, then we now have an equation for L, which is what we're looking for. Okay, L means looking for. Okay, so all we need to do is to cross multiply. That will give us, of course, a quadratic equation for L. So there might be two roots, unless we're lucky, which is what L really stands for. Okay, multiply through, you get Sn squared minus 2L Sn plus L squared is equal to Sn plus 1 Sn minus 1 plus L squared minus L times Sn plus 1 plus Sn minus 1. Do you agree? And look what happened. L canceled out. It was fake. It looked like it was going to be a quadratic equation, but it isn't. It's just a linear equation for L. And the solution is Sn squared minus Sn plus 1 Sn minus 1 divided by 2 Sn minus Sn plus 1 minus Sn minus 1 is L. Got it? You see what we did? So we have just calculated the limit. Now, of course, this can't be exactly right. Why is that? Because this is just a model of an oscillating sequence. So this here is a model of an oscillating sequence. Okay, it's just a model. But it says if the sequence behaves like this, then the limit of the sequence is given by this formula depending on the nth term. So now Mr. Shanks makes a brilliant jump. He says, suppose we have a sequence of partial sums, Sn. Okay, that is, S1, S2, S3, and so on. And they're tending to the limit L. He makes a model, and then he says, let's take a Shanks transform of the sequence. So the Shanks transform of this sequence is a new sequence. We'll call it S1. Sn, which is defined as exactly what I wrote down before, Sn squared minus Sn plus 1 minus Sn minus 1, divided by 2Sn minus Sn plus 1. Oops, this is times, minus Sn minus 1. Okay, this times that. Okay? So this is definition of a new sequence. Okay? So this gives us S11, S12, S13, and so on. But not really S11. Why is that? Because to calculate S11, we would need S0, 1, and 2. But I said we only have S1 here. So this sequence begins, oops, we wrote it here. S1, 2, S1, 3. Okay? Now we do it again. When we make a new sequence, blah, 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 blah. Here's the second Shank sequence. S3, S4, S5. Okay, so here's the second Shanks sequence, and then we can make a third Shank sequence, and we can continue doing this. Let's look at those Shanks sequences. Let's see how they come out. Okay, so can you lower the screen? Is there a way to?
Yeah.
Oh, good. It's opening up. That's great.
It's warming.
Okay.
Yeah, the projectors might be on the screen. Yeah, but
Do you push some buttons here to make?
She's gonna do it from the controller.
Oh.
The HDMI button.
Okay.
Is this like okay?
Yo, this is great. So how do you like it so far? Do I have to tickle this?
Yeah.
It's yeah. Maybe
Push the screen. PC?
It should put dark should be if it's connected dark.
Oh, it was.
Ah, good. Okay, super. Okay, there. See, that's how you spell Shank. That doesn't have much information on it, but let's. Okay, so now here is the sequence that we're looking at. Okay. Now, if you talk to the average guy in the street, the guy says, by the way, this is the sum of the sequence. This is 0.693. This is the log of 2. 0.693, 1472, blah, blah, blah. Okay? Now, if you listen to the guy on the street, what the guy says is add up the numbers. So these are the partial sums. A. Those are the partial sums. So they go 1, a half, blah, 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 blah. So after 8 numbers, we're supposed to get 0.693, but after 8 numbers, it's 0.634. And after, say, 1 million numbers, it's accurate to about 3, maybe 4 decimal places. 3 decimal places. It's never getting there. On the other hand, if you take a Shanks and you look at the sequence of Shankses, by the time you've gotten just to the 3rd number, The information is already there, and it already knows it's 0.690, 0.694, 0.692. Here it is, 0.693, 693. So by the time you use just 7 terms in the series, you have already gotten it correct to 1 part in 1,000. On the other hand, if you take a second Shanks, it goes 0.693277. Look at that. And if you calculate the third Shanks, we have already got 0.6931467 instead of 6931472. Now, to calculate this Shanks, you need to know these 3 Shankses, and to know these 3, you need to know all of these 5, and to calculate these 5, you need to know 7. So from just the first 7 terms in the sequence, I know the answer accurate to an error of just 1 part here, 1 part in, well, in a million, from just the first 7 terms. Okay? So the information is in the series, and we just have to coax the information out of the series. Of course, you can be inefficient and add up the series, but we want to get there fast. Okay? And what Mr. Shanks tells us is that by making an asymptotic model, we can extract the information. A really interesting problem is this the best way to do it? Of course not. Okay? There are an infinite number of ways that you might be able to extract the information from the series. The question is, how do you determine the absolute optimal way? And that's a very deep problem in information theory and statistical mechanics or statistical physics. And the answer is not no. If you find this interesting, you might want to look at it. Okay? But my point is that one way of getting the information out of a series is to sum it up. But it couldn't be dumber. Okay? Now let me show you something else. Here is an even more difficult series. Here is the series 1 over the square root of 2 plus 1 over the square root of 3, square root of 4, and so on. Okay? This is a very, very slowly converging series. You could never sum this series by adding up the numbers. It's absolutely impossible. Can't do it. Just completely impossible. Even if you have a hugely parallel computer that's working night and day for weeks and weeks, you can never do it. However, if you calculate the Shanks transform of these partial sums, here's the first Shanks, here's the second Shanks, here's the third Shanks, and we already know that the answer is, just from this first 7 terms in the series, we know that the answer from this Shanks is 0.60490 instead of 60489. In fact, 604,898, and here we have 604,900. So it's accurate to about 1 part in a million. So the information is there, and we just want to get the information out quickly. Okay? This is one possible way of doing it. Okay, you have a question?
Well, so how does this actually work for all alternating series, or can we test in some way for which
No,
series it's
because you could make a new alternating series. You could be a very nasty person. Okay? I know you're not a nasty person, but you could be a nasty person because you could define a new series, right, where the 1300th number in the series is pi. Okay? And obviously, the first 1200 coefficients in the series don't know about pi. They don't know that pi is coming up. So the problem with rigorous mathematics is that this is not a uniform thing. This can't work. This can't be correct in complete generality, because you can always make a counterexample. But you see, we're not mathematicians. Except for him. But we're not mathematicians, we're physicists, and physics is not physics problems are not nasty. They're not out to get us. They're not out to fool us. They're very hard problems, and we don't know how to solve them analytically. Okay, we're trying to solve hard problems, and in physics, it rarely happens that the 10th term does something strange. That typically doesn't happen. So typically, the series have a kind of uniformity to them, and something strange doesn't happen at 15th order in perturbation theory that screws up these attempts at getting the answer from the first 7 coefficients. Okay, so this series has a kind of uniformity. You understand what I'm saying? There's a kind of smoothness to this kind of problem. And when we do perturbation theory, typically the perturbation series comes closer and closer and closer and closer to the answer in a kind of uniform way. It's oscillating about the answer, getting closer and closer and closer. And we are looking for non-rigorous ways of extracting the information with tremendous efficiency. But I don't, under any condition, claim that this is the only way to extract the information. And tomorrow I'm going to show you another way to extract the information. But there's another thing that I have to show you tomorrow, which I promise you you're going to love. This was a way to accelerate the convergence of a series that was already converging. But how do we accelerate the convergence of a series that is diverging? Okay, and I'm going to show you how to do that too. Okay, so in other words, I claim that even if the series is diverging, the answer is buried there in the series. The answer is there. It's already there. Hard to believe, but it's already there. Okay, and we have to develop techniques that are indirect ways of extracting the information from the series. Yeah?
I guess that would be useful for understanding common field theories and why.
Absolutely. So the point is that when you solve a quantum field theory, the only analytical tool we have is to develop a series. In this case, it's a series of Feynman diagrams, okay? And first, and they're organized by the number of vertices in the diagram. So we sum up all the diagrams with one vertex, then all the diagrams in a phi to the 4 theory, right? For example, if we're summing up a G phi to the 4 theory, all the diagrams with one vertex, there's only one of them. It looks like an infinity, okay? Then, so this is first order in perturbation theory. Then we write down all the diagrams with 2 vertices, and there are 2 of them. Okay? This is a 4-legged spider doing push-ups on a mirror. Mickey Mouse hat. Okay? And then all the diagrams with 3 vertices. So there's one that looks like this, and another that looks like this. Okay? And then there are altogether there are 4 diagrams. There's another one that looks like this, and then there's another one that looks like this. That's a re-entry theory. Okay? And so on. And then in 4th order there are 10 graphs. And in next order there are about 29 graphs. Nobody knows a formula, by the way, for the number of graphs. There's no known formula for the number of graphs, but it's a very interesting question in combinatorics. And when you add up these amplitudes, okay, this is the first term in the series, call it A1, here's A2, here's A3, here's A4, and so on. That is a divergent series. And we have to know how to sum that series. If you don't know how to sum the series, what's the point of learning Feynman diagrams? It's a divergent series. Doesn't, if you think that a divergent series doesn't mean anything, then what's the point of doing that?
What do you mean by sum a divergent series? Are you trying to
We have to
figure out how
define
rapidly
that.
it
We have to,
diverges or something?
we have to define what it means to even use the word sum. Okay, so tomorrow I'm going to begin to explain to you, this is just this is just the beginning, okay? And I have to explain to you summation theory. By the way, as you might have guessed, summation theory is partially rigorous, but mostly not rigorous. Okay? So it's very powerful, and it works in places where people cannot even justify why it's working. Okay, so we don't, I mean, this is, I'm teaching you, you know, cutting edge mathematical physics, very useful mathematical physics, and it isn't even known in some cases, why it's working. This has worked for you. If you're interested, go to work. Okay, yes?
How do you know when you use these methods and you get an answer that it's...
That is right.
Yeah.
Exactly. It's a very, very good question. And the answer is, asymptotics in general is self-referential. If the numbers appear to be approaching a limit, then it looks like that must be the right answer. Okay? But typically, we don't know the right answer. So we just have to hope that it's, you know, if you're using the wrong technique, then typically these numbers are bouncing around and they don't converge to a limit. They just don't, they're bouncing around. And we know that the Shanks model that we used over here, the model of the Shanks that we used, is not a good model for the behavior of the series. It wouldn't be if the series, for example, doesn't have an oscillating partial sum. Next time I'll start out by showing you a series that does not have an oscillating partial sum, and therefore Shanks is probably not going to be a good idea, so we use Richardson. You may not know it, but you have used Richardson